Let's talk about phase changes and the math that goes with that. Our objectives will describe what happens during a phase change on a molecular level, and we will use Q equals m delta H in calculations. All right, so let's talk about phase changes. During a phase change, heat is added, but the temperature stays the same. I'm going to say that again. During a phase change, heat is added, but the temperature remains the same. So what is happening during these phase changes if that's the case? Let's first take a look at the molecular view of solids, liquids, and gases. What are the differences between them? So in a gas, the molecules move independently of one another. They can fill any volume they're in and are very compressible. A liquid will take the shape of the container it's in, is slightly compressible, and the particles interact. These interactions are called intermolecular forces. They're not very strong, but there are a lot of them per molecule. And finally, solids have stronger intermolecular forces. They have a rigid structure, which is not compressible and has a fixed shape. So when you go through a phase change, you're changing the order of the particles in the intermolecular forces. Essentially, by adding heat, a solid's rigid structure shakes apart when the molecules start to vibrate faster. So you're heating it up, the temperature's going up, it means it goes faster, they're shaken, and they shake apart. Okay, so when you add heat to a liquid, the molecules completely escape those intermolecular forces as attraction between molecules. They become free agents, which are a gas. The math that describes this relationship is Q equals m delta H, where Q is the amount of heat, m is either mass or moles, and delta H is the heat of the phase change. And there will be a subscript on dH, which indicates which phase change you're dealing with. We'll get to that in the next slide. Okay, and make sure that your units match when you're using this equation. Now I also have the note here, energy out is positive, energy in is negative. So if you have to add energy into the system, your sign for delta H should be positive, your Q should be positive. If you have to take energy out of the system in order to make it happen, so for example, if you're going from a gas to a liquid, you have to cool it down, then your Q is negative and your delta H is also negative. So what do I mean by these subscripts? Delta H VAP is the amount of energy you need to transfer to do a liquid-gas phase change. It's called evaporation or condensation, depending on which way you go. Delta H VAP applies for evaporation, and it's equal to the negative for condensation, because if you're condensing, you're pulling energy out. Delta H fusion is the amount of energy you need to transfer to do a liquid-solid phase change. So that is melting and freezing. FUS is short for fusion. So again, they're opposites of each other. If you are melting, you have to add energy and it's positive. If you are freezing, you have to take away energy and it is negative. And finally, we have delta H sub, the amount of energy you need to transfer to do a gas-solid phase change, which is either known as deposition, when you're going from a gas to a solid, or sublimation, where you're going from a solid to a gas. And again, if we're going from a gas to a solid, it's negative. We have to take energy out. And if we're going from a solid to a gas, it's positive, because you have to put energy in to make that happen. All right, so let's try a calculation. We're going to do a phase change calculation. I'm calculating Q. How much heat does it take to melt 3.97 grams of water with a delta H of fusion of 6.0 kilojoules per mole? Now, when I'm reading this, the first thing I notice is that we've got grams here. We've got kilojoules per mole there. That is not a match. So I'm going to convert 3.97 grams of water into moles of water. We do that by looking up the molar mass. Use the periodic table. Let me say, how much does hydrogen weigh? It's 1. How much does How much does oxygen weigh? It's 16, so if you take 16 plus 2 for 2 hydrogens, you get 18 grams. And when you run the math on that, 3.97 divided by 18, you get 0.221 moles of water. All right, so at this point, we have an M that matches our delta H, and we're going to put this sucker together. So how much heat does it take to melt? So for melting, we are adding the heat in, and it will be positive. So Q is heat. Terrible Q, but we can still read it, right? We're going to take our 0.221 moles, and we're going to multiply it by the delta H of fusion that we were given, which is nice and easy, 6. That is actually what it is. By the way, that's not a made-up number. It is exactly 6. Okay, so if we do that math, we get 1.33 kilojoules. It takes 1.33 kilojoules to melt 3.97 grams of water. Okay, so now we have solved for Q. Let's try something else. How many grams of water is formed when you pull 25 kilojoules of energy from 15 grams of water vapor? Delta H vap is 40.7 kilojoules per mole. So a couple of things to see here. We've been given a mass, but it actually asks us to solve for a mass. This is a red herring. That 15 grams does not matter. I repeat, that 15 grams does not matter. Additionally, we're saying we're pulling, which means we're taking the energy away. And if we're taking energy away, then delta H vap will be negative. So here we go. Negative 25 kilojoules is equal to M times 40.7. Then we do the algebra thing. We divide both sides by 40.7, and we get, well, negative 40.7. I apologize. So we will get a positive number of moles, which we will then have to multiply by 18 grams per mole in order to get grams. All right, so let's do this thing. If we divide 25 by 40.7, we get 0.641. And you'll note I didn't mention the negative signs because you can actually cancel your negative signs. If you've got them on both sides of the equation, they cancel each other out. All right, so now I've got 0.641 moles, and I multiply it by 18 grams, and I get that 11.1 grams condensed. All right, which is not the total of 15 that we started with, but it's up there. It's a decent amount of water. All right, so let's try another thing. Calculate the heat of vaporization of an unknown material if it makes 24.9 kilojoules of energy to evaporate 2.5 grams of unknown. So here we're dealing with positives, and we're not going to be able to get molar mass because it's an unknown. We don't know what it is. So we're going to go ahead and plug this stuff in. So it says that it takes 24.9 kilojoules to evaporate the thing. And on the other side, we have 2.5 grams times delta H vap. If we divide both sides by 2.5 grams, we end up with 9.96, which we're going to call 10, because we only have 2 sig figs. I'm going to put a period after the 10 to indicate that that is in fact 2 sig figs, kilojoules per gram. So that is our delta H VAP. So none of these are super hard, but we do have to be conscious of whether we're going to be positive or negative for our energy change and for our heat change. And we need to make sure that our units match or we will not get it to work. So to summarize, in a phase change, the heat is added and temperature stays the same. Or it could be taken away. Temperature stays the same, either way. Energy out is negative, energy in is positive. Delta H VAP is for evaporation and condensation. Delta H fusion is for melting and freezing, and delta H sub is for deposition and sublimation. Finally, Q, heat, is equal to M, moles or mass, times delta H, which is going to be one of these vaporization, fusion, or sublimation ones. Okay, hopefully that was pretty easy for you to follow. We're going to get slightly more complicated in the next one.